Just a couple of quick comments about the homework that you did. I'll turn these back to you after class. A couple of obvious things. Part of it is showing your work. I appreciate it when you, it's very telling to me when people don't show any work, they put down the answers, and it's also then telling when they get the answers wrong, and other people in the class who also just put the answers get the same answers wrong. You know, there's kind of doesn't take a lot of Sherlock Holmes kind of work there to figure out what's going on in those kind of cases. So, so it's not just simply so I can find out who's merely copying, because frankly, you could all just copy each other's complete work. But even if you do that, at least you're embedding the process into your head. So if you're smart enough to do all the work in your head without showing any of the work, then submit yourself to the process of, okay, I'm going to go through my thought process, I'm going to write it down as I go, because ultimately it's going to benefit you in the end. I told you before, if during the exam you have the right answer, but you don't show any work, then there's no partial, I could argue that you probably shouldn't get credit for the answer. But think of it this way. If you write down the answer and show no work and you get it wrong, I don't have an opportunity to give you any partial credit, do I? It's either right or wrong. So if we have a 10-question test, each question's worth 10 points, you write down the answer and you put the decimal place in the wrong place, you're at a 90. If it's a 5-step process and at the very last step you messed up one small thing, you might lose 2 points. So if it's worth it to you for that other 8 points for the exam to show your work, which you've got to do anyway, whether it's in your head or on paper, show it to me. Show me all your work. That way I can, for example, when you get these back, I can see, for those of you that wrote down your conversion factors, I can show you where your statements of equality were wrong, or how you inverted the conversion factor. You have the numerator, which should be the denominator. You should take it and flip it, and then it would work. See, I can see that when you show me the work. When you don't show me the work, it's either right or wrong. I can't help you anymore. So please show your work. The first question, I know I emphasized that light is outside of the scope of our course. On question number 1, there were 2 answers. The other one is heat. And we can argue about that, but rather than thinking of it simply as light, recognize that energy doesn't have any matter, right? There's no mass to energy. So in the first question, light and heat. I didn't take off for it, I wrote it down for you, because I know I emphasized light in here. Part of that is language as well. Later on we're going to talk about light energy, or the light spectrum, or the energy spectrum. We're going to talk about radio waves as light. We're going to talk about microwaves as light. Because light is really a phrase that talks, we generally think of it as a band that we can see, but it really is much broader than that. So a lot of scientists refer to electromagnetic energy as light's part of that electromagnetic spectrum. Some people use the word light, and it refers to all different kinds of electromagnetic energy, not just simply what we see as light. Okay, so include that in your thinking as well. Yeah, I did get the opportunity to write Smurfs on a couple of them. That was cool. So other things, they're minor, some of the setups, but hopefully you'll see that. Anything else in particular? Usually it's just conversion factors and not showing your work. So I encourage you, remember, always show as much work as you can. A few of you went to complex conversion factors. I don't know whether you looked them up or computed them on your own. You didn't take a 2-step process. You went directly from kiloliters to milliliters and things like that, and a few times you didn't do it right. So if you'd just done the 2-step conversion using statements of equality, you might have been a little bit more successful. All right, let's go ahead, since we have a little less than half an hour now, and today is another one of those meaty subjects in that this is the kind of stuff that's going to haunt you for the entire course if you don't get it down now. Okay, and we're going to answer some of the questions that we kind of posed earlier on. We're going to go back to our discussion of accuracy, precision, and significant figures. Recall this image from class, and I'm kind of making an analogy, that accuracy is this whole idea of how close to being correct, true am I? How close am I to hitting the bullseye? If the right answer is the center of the target, how close is my measurement to being at the center of the target? That's the concept of accuracy. Precision on the bullseye is how tight your pattern is, right? So the tighter the pattern, the more precise. The closer to the bullseye, the more accurate. They're not exactly the same thing. They're two concepts which kind of cooperate. You know, if I have good accuracy but poor precision, I have a large pattern which none of them may be in the bullseye, but yet the center of mass of all of them would be the bullseye. We're hoping to actually hit the bullseye, right? And hit it repeatedly, which means we want to be both accurate and precise. We mentioned that determining, we compare the value, what it should be. We're told, hey, measure this length. You give me a length. I tell you, well, I know, because in this class I'm God. Not really, just, you know. Somebody outside of ourselves comes up and says, this thing is 3 meters long. And you measure it and go, no, it's not. It's 2.89 meters long. And I go, you're off by 0.11 meters. You're off. How do you know? Because it is 3. And you didn't get 3, so you're not as accurate as you could be. You say, but you gave me a bad ruler or a bad yardstick or something, right? Okay, that's a precision issue now. That's a different thing. What process did you use? How well did you use the equipment that you were given? And then what is the ability of the equipment? So we're using this idea. So we compare it to correct. In determining the precision, what we're going to do is look at the number of significant figures. Remember I said how many figures you have is important because it communicates in science that you have the instrument that makes that measurement valid. You can't make it more precise than you can legitimately indicate. For example, 2.545 centimeters, do you see that that's more precise than 2.54 centimeters? I've got a place to the thousandths place. On this other measure, 2.54, I'm going to the hundredths place. Now, what does that tell me about the instrument that I use to get these measurements? To what place did this instrument measure? Anyone? Go ahead. Okay, that would be the obvious answer, which means it's wrong, right? Because we're supposed to estimate the next digit out. If you assume that this person did it correctly and came up with 2.545, how far did the instrument measure? 2.54. And they estimated it's halfway between 4 and 5, therefore it's 2.45. On the measurement of 2.54 centimeters, it measured out to the tenths place because the operator, the individual, estimated a 4 in the hundredths place. They looked at it and said, it's a little bit less than halfway between 5 and 6. So it's not 2.55, I'm going to say it's 2.54. Why? The instrument gave me 2.5. I'm adding the next place out. Okay, so the one on the left is more precise. Hopefully you're starting to realize that the instrument on the left probably costs more because the precision is costly. I can take it even more precise than that, but every time I increase the precision, I increase the cost of getting that more precise number. This is where we talked about before, where 2.5, 2.50, 2.500, it's not the same thing in science. Hopefully you see over here that 2.500 and 2.50 in math class, you might say they're equal. Well, they're equal in value, but they don't communicate the same information. This first one tells me that I had an instrument that measured out to the hundredths place and I estimated the thousandths place. On the smaller measurement, or the less precise measurement of 2.50, I only had an instrument that measured to the tenths place and I estimated to the hundredths place. Which one am I going to trust if I'm the same operator and I get the same basic accuracy? Which one am I going to trust more? The one that's more precise. Which one am I going to use? The most precise one. Now, if I say that I take a yardstick and I measure it to be 2.500000 meters, and all I have is a yardstick, I'm a liar. Because I can't measure it that precisely. I've just made it up. And yeah, I know that's one of the critics of science, make up stuff all the time. But in actuality, we don't want to do that. So when you put too many places of precision, you're misinforming, you're leading people astray, because it matters in science on how many significant figures you include in the measurement. Okay? Principle good? Because we're going to move on to the 4 rules of determining significant figures. And going forward, I'll probably just say sig figs because it's fun, first of all. You don't get to use the word fig in sentences a lot, and shorter, and I have a speech impediment, so the fewer words, the shorter words, the better. The 4 rules for determining the significant figures, the sig figs. You have to remember these rules and use them virtually every problem you do from here on out. This is big deal stuff, okay? And it can be a pain for everybody. So here we go. First, and just accept these rules. Just get them down. They're in your book. They're listed on page 23. So if you don't get them down now, get them down from your notes. They're in blue, so as you do your independent study, it'll remind you, hey, you need to know these things. But first of all, non-zero digits are significant. If it's a 1, a 2, a 3, a 4, a 5, a 6, a 7, an 8, or 9, it is by definition a significant figure. Okay? It's always going to be significant. Second, zeros to the left of the first non-zero digit are never significant. It is not significant. So we've got definitely 1 through 9. They are always significant. Zeros, if they lead the number, are not significant. You get the difference? They have to be to the left of the first non-zero. If its 0 is to the left of a first non-zero, it is not considered significant. I always hate saying that one because I know you don't like to tell anybody or anyone that they're not significant, right? Sorry. Like that pizza commercial, you know? But that's my dream. Sorry, kid, it's been done. So, non-zero digits are always significant. 0 digits to the left of the first non-zero digit are never significant. And now we get to play a little bit, okay, now conditional clauses. Here we go. Zeros between significant figures are significant. We're going to work some examples and some on your own real quickly as a class to reinforce these ideas. But I'm going to repeat all 3 of them and then all 4 of them again. Non-zero digits are significant. Zeros to the left of the first non-zero are not significant. Zeros between significant figures are significant. And lastly, zeros to the right that are also after the decimal point are significant. Okay? Zeros to the right after the decimal point are significant. The trailing zeros are significant. So in 2.5 or 2.50 or 2.500, that is 2, 3, and 4 significant places respectively. And we'll see that with some examples. So right now in your notes, get comfortable of not only knowing these rules, but walk through it in your mind every time you do a problem. How many significant figures should be in my answer? It'll matter. Because that's where a 2.5 might be true, but a 2.50 is correct. Because they're not the same number, even because of the difference of how many significant figures you're showing in your answer. And we'll have rules on how to figure out how many you have to have. They're going to follow after we get comfortable with determining significant figures in a number first. So, example 1.5 gives us these. Significant figures. How many significant figures are in the number 3.234? And actually for this exercise, I think we're going to do better with using a white marker. So let's see if the board underneath is clean. Hopefully it is. Yep. It's public space, sorry. I'm not going to do that much work in advance to get rid of stuff. It's on YouTube forever. All right. So, 3.234, how many significant figures are in that number? Let's go through the process. What's the first step? What's the first rule say? Go ahead.
Non-zero digits are significant.
All non-zero digits are significant. So, that's non-zero, that's non-zero, that's non-zero, that's non-zero. Do I have any other to deal with? No. How many significant figures are there? 4. Because they're all significant. Based on the first rule alone, they're all significant. Second number, 6.016. Let's walk through the 4 rules. All non-zero digits are significant. So this is significant, this, and this by the first rule. The second rule, all zeros to the left of the first significant number, first non-zero number, are not significant. Well, there aren't any, so we don't have to apply that rule. Third rule, all zeros between significant numbers are significant. The zeros between the first 6 and the 1, which are both significant. So we're done, right? We've accounted for every single digit. So how many are significant? Again, 4 are significant. 105.340. First rule. Non-zeros are significant. Second rule. Leading zeros are not significant. We don't have any. Third rule. Zeros between significants are significant. Fourth rule. Trailing zeros are significant to the right of the decimal place. How many significant figures? Just 6, yeah. The fourth one? Here we go. Here we go. First rule, what is it? The first rule for determining, just go ahead and give it to me. We're a small group. I'll let you do some quick answer. Go ahead. Non-zeros are significant. So the 4, the 5, and the 1, right? Those are non-zeros. Second rule, somebody from the first row. What do we get? What do we do next? So the second rule is
Zeros to the left of the non-first zero are not.
zeros to the left of the first non-zero are not significant. Sorry, for this, you don't matter. Those are non-significant. Third rule, second row. Somebody? Ma'am, go ahead. Intermediary zeros, or zeros between significants, are significant. These two are between the 5 and the 1. Therefore, they're significant. Fourth rule. Ma'am?
All zeros at the end of a number and to the right of the decimal point are significant.
Trailing zeros are significant. Is the way I shorthand that. Trailing zeros are significant. That's significant. Any left over? How many do you count up that I've underlined indicating they're significant? Yay, we did right. 2,330. Let's walk through it quickly. Non-zeros. Leading zeros, none. Zeros between significants, none. Trailing zeros to the right of the decimal place, none. You see that? Trailing zeros to the right of the decimal point. There is no decimal point there, is there? So this is not a 0 to the right of a decimal point. There is no decimal point. So, are we done? Yeah, we're done. How many? 3. There's only 3 significant, 3 sig figs in that one. Okay? 3 non-zeros, no leading zeros, no intermediary zeros, no trailing zeros right of the decimal point. 3 is all we have. And before we go to on your own 112, and we're going to do it just in the same way. So you can see them on in your book. We're just going to go through it the same way we just did this one. We're going to take the numbers on the side and say how many significant figures are there. Let's go through the process again. This first number, non-zeros are significant. Leading zeros are not significant. We don't have any. Intermediary zeros are significant. We have 1. That's in the tenths place. Trailing zeros to the right of the decimal place are significant. How many? We have 1, don't we? Trailing 0, and it is to the right of the decimal. Therefore, we have all 5 figures are significant. Let's walk through the rules. Every time, just walk through the rules every time. First, non-zeros, 1. Leading zeros, which are not 3. Intermediary zeros, we don't have any. Trailing zeros right of the decimal place. Significant figures, 2. Do it on your paper. Come up with a number. Look at me when you have it, and then we'll do it together. So I can see your bright and shiny and or otherwise faces. Okay? We got most everyone. Here we go. Non-zeros. 1, 2, 3. Leading zeros. None. Intermediary zeros. 2. Trailing zeros right at the decimal place. 1. 6 places. They're all significant. Go. Same deal. Look up here when you have a number for how many sig figs. Don't even need to write it down, do you? Nope. I'm not going to show my work either. No, I'm kidding. So it's going to be either right or wrong. No. This is just the way I do with the lines. One thing I'll remind you of is after you do all 4 of them, it's a good idea to go back and check the number if there's anything that's still left unmarked, either crossed out or underlined, and see if it's a 0 that's between significant figures. Occasionally, when you work this out, you'll find one that's not accounted for. Just run through the rules one more time, but especially the rule that says zeros between significant figures are significant. You can always run the rule multiple times, like a computer program. Run it once. Oh, I've got something unaccounted for. Just run it again. Yes, ma'am?
How many zeros can be between the significant figures?
As many as there are. An infinite number could possibly be there. How's that? Or twice as much would still be infinite. So, or 3 times, well, that's still infinite. So anyway, so 61.054, running through the rules. The non-zeros are significant. Leaders, we don't have any. Intermediary, we have 1. Trailing, we have none. They're all accounted for. 5. Last one. 300,000 millimeters. First rule, non-zeros. The 3 is significant based on the first rule. Second rule, leading zeros. We don't have any. So we can't mark those off as being insignificant or non-significant. Third, zeros between significant figures. We don't have any. Just 1. There's nothing between that, right? Lastly, zeros to the right, trailing zeros to the right of the decimal place. We don't have any. So there's just 1. 1 significant figure in 300,000. Do you see how it changes everything if that was 300,000.0? If it was 300,000.0, we'd now have 7 significant places. Because right now, I'm telling you that I have an instrument that can only measure with, it's a very imprecise measurement. I can only measure out to, this huge number. I've got this, never mind. But if I put a 0 in there at 0.0, that lets me know, oh, wait a minute. This number is actually coincidentally just very much close to a whole number because the decimal 0 indicates that I can actually measure that out to the ones place. Here I can measure it out to the 10,000ths place. But there I could measure it to the ones place if I have a 0.0 at the end because I estimated that it's actually on the mark. You see? So a lot of information by adding a 0.0 at the end because it makes every one of those significant. That's what I'm talking about before we do the rules. If you run through it once and you've got unaccounted for digits, run through them again because what probably happened is you said something else was significant and you've got something in the middle that became significant because it's between significance, and that's a 0. Look on page 24 to the ruler there. And this is, that's me. Excuse me. That's annoying. It's more annoying than a buzz. I have the misfortune of having a phone carrier that has 2 numbers associated with my number. One is the number that everybody calls, and the other one is the number that they keep for administrative purposes. Well, that secondary number that I've been assigned used to belong to someone who managed real estate. So I get tons of calls for people wanting to rent an apartment. So unless you are on my contact list and I see a name pop up, I am not answering the phone. By the way, none of you should have my cell phone anyway, so it shouldn't be an issue. But anyhow, on page 24, they show a ruler, and they're trying to make this point here about this idea of, actually I flipped the page a little bit too soon. Keeping significant figures. If it's very important in chemistry, when we keep all the significant figures that you can, it's really important when you're doing experiments. Again, you've paid for, you've invested in that material, it matters. So on this ruler, they show that we're looking at it. Let me recall what the point is here. See that it goes from the 1 to the 4. As you look at that, remember the way we do it, we start on the first mark, not on the 0 mark, on the 1. We read that. We know that's going to be about 3. When we look more closely, I see that it can be marked off into tenths. So 3 point something, right? I can get that straight from the measure. 3 point something. Oh, it happens to be right on the 4 mark, which means it happens to look like exactly 3. So by the ruler, I could say that was not just 3, that was 3.0. Oh, but now I need to estimate at 1, right? So I can look at that ruler and say it's 3.00. See, I can do that with authority because the instrument will give me to the tenths place, my estimation will take it to the hundredths place. So 3 and 3.0 and 3.00 are not the same number. And by using this rule of precision, I can get a more precise number. And in chemistry and in all sciences, I want to be as precise as possible with my measurements. Because if I say it's a 3, well, it could be between 2.5 and 3.4. It could be anywhere in there. If I say it's 3.0, now we know it's somewhere between 2.95 and 3.05. When I say it's 3.00, I'm even more precise. My region of actual length is much smaller. Yes, ma'am?
Like the ruler enters, would you rather enter decimals and fractions?
Well, that one is a metric, I believe. Oh, it's centimeters? Yeah, so it's metrics, it's in tenths. You're going to be working in metric. You're not going to be given feet, so it's all going to be in tenths. So 3.1, 3.15, 3.153, it's going to go like that. I do have more stuff for us to do in scientific notation, but we're not going to go there today because with about 3 minutes, how much scientific notation could we get done? That was meant to be up there at the end. Again, I'm just jumping through. I know in the video it's going to be all wacky, but just to make sure you've got this heads up for what's coming up. And you are dismissed when the bell rings.